Welcome everyone to one of the McDonald's Observatory live streams. So today we're going to be celebrating the birthday of the Hobby Eberly Telescope, one of the largest telescopes here, and it turned 25 years old this month. So it's pretty a young adult at this point. And yeah, my name is Saul Rivera. Some of y'all might already know me as being one of the hosts from the previous times. But tonight we have some of the staff that work on the Hobby Eberly Telescope here to talk to us about some stuff of the telescope and what they do on the telescope. And again, there will be mods in the chat to answer any questions you have. And also at the end, we will do a Q&A session, but feel free to drop questions throughout the program if there's something you want one of us to know. And with that, I'm going to pass it over to my colleagues so they can introduce themselves. And Jim, how about you start us off?
Hi, I'm Jim Fowler. I'm the head of computer operations at the Hobby Eberly Telescope. I've been there for about 25 years now. Basically the entire operational history of the Hobby Eberly Telescope. Over to you, Herman.
Okay, so I'm Herman Creel. I'm the facility manager of the Hobby Eberly Telescope. I joined the HET in 2009, so I'm basically here, what's it now, my 14th year. You notice from my accent that I'm not originally from here, so I came over to the HET from South Africa, where I worked on the Southern African Large Telescope. So have a little bit of a telescope background when I joined here. I also worked in the military product development field for many years, 18 and a half years, infrared air-to-air missile systems before I got into the telescope business. So glad to be here at the HET and looking forward to many more years with the team.
Cool, and I'm Stephen Janowicki. I'm the science operations manager here, responsible for the scientific output and productivity of the telescope and keeping everything with the researchers running smoothly. I am very young by comparison in my experience to the HET. I've been here only 4 years, so I'm still learning a lot. But it's an amazing telescope, like Saul mentioned, the biggest here at the observatory, and it's amongst the very largest optical telescopes in the world. So we're all very fortunate to be here celebrating its 25th birthday, and many more to come. A facility like this is built for decades of productivity, and I think we're hitting our stride. And it's 25. The telescope looks great at 25. So yeah, happy to be here and chatting too.
Thank y'all so much for joining us tonight. And we'll have to start off. We want to talk a little bit about the history of the Hobby Eberly Telescope. So to talk a bit about that, I'm passing over to Jim.
No, thanks, Saul. The Hobby Eberly Telescope really began in 1980. Harlan Smith was the director of the observatory at that time. And he was interested in building another large telescope. He had built the 107-inch. It was dedicated in 1969. And so it was about 10 years old at this point. And it was getting a little long in the tooth. It was no longer one of the biggest telescopes in the world. And so he wanted a larger telescope. He began dreaming about a 300-inch telescope. He called it the Eye of Texas. And there were a number of colored glossy brochures put up, and he talked it around here in Texas and tried to get partners. It was very difficult to do fundraising at that point, and he never did get the funding for that 300-inch telescope. In 1989, Harlan retired. Frank Bash took over, and in 1991, Harlan passed away. But Frank Bash started continuing that effort to build a large telescope. He talked to some of the folks at Penn State University, Larry Ramsey and Dan Weidman. They had an idea for a large, inexpensive telescope that they thought could could be built very inexpensively. Basically, with a segmented mirror telescope, they were planning on building a 4-meter, putting it in a grain bin, getting graduate students or undergraduates to polish the mirrors under the football stadium, a classic place to do your science experiments. Texas told Penn State, if you really want to do this, you need to make it really big. And so we proposed a 10-meter telescope to Penn State. In 1994, the formal agreement was signed between Penn State, the University of Texas, and the planning began for this telescope. Groundbreaking occurred in 1994, and you can see from the construction pictures how the telescope was built. This picture shows how the pier of the telescope was being smoothed so that the telescope could ride on a very flat surface. We began first light in 1996, December of 1996. We found our first star with the telescope. We still had a lot of construction to do at that point. In December of 96, we also hired our first site manager, John Glaspie. In 97, he hired me. I was the second employee here. And John and I worked on the telescope with Bill Wren, who some of you from the Visitor Center may know. He was one of our early telescope operators in those days. We had a dedication in October of 97, and that's the 25th anniversary that we're celebrating now. We still had a lot of construction to do, a lot of testing and work on the telescope. The first instruments came in 1999. We began full-time science in October of 1999 and have been doing full science ever since. We only had a limited set of instruments at that point. Low-resolution spectrograph was our primary instrument, and medium-resolution spectrograph followed soon after that. In 2001, we obtained the high-resolution spectrograph, which became a workhorse instrument here. We continued doing science until 2014, when we shut the telescope down and took off the top end, replaced the tracker, replaced the instruments with new ones that Stephen will describe. We went back into science operations in 2016 and really full-time science in 2018. And we've been doing science every night, basically, since 2018. That's your quick and dirty history of the Hobby Eberly Telescope.
All right. Thank you so much, Jim. That's super cool info. Now, here to talk to us about kind of some of the engineering that goes on with the telescope, I'm going to pass it on over to Herman.
Thank you, Zol. So there you see the Hobby Eberly Telescope, and you can recognize that from some of the construction pictures. It looks more or less what they tried to do there. And I'll just point out at the back of the telescope, you can see there's a black tower sticking out there at the back. That is called the Center of Curvature Alignment System. There is an instrument up in that top of that tower that we use to align the primary mirror. As Jim mentioned, we have a segmented mirror, and we need to align that those 91 segments to form a perfect sphere when we go on sky at night. On the front left there, you see what we call the G-tag. Jim, you'll have to help me what G-tag stands for, but that's our visitors lobby. And for those who haven't visited the HET yet, please come to the HET. It's open to the public. You can walk through there. There's interactive exhibits there, and you can also look through a window and you can see what's going on the telescope floor. To the right, go ahead.
Sorry, that's the George T. Abel Gallery.
That's correct, and that was
gave the money to build the visitors gallery there.
Correct, yeah, that's right. And that part of the building that stands out at the right, that is what we call the receiving bay. And we also have our mirror coding lab in that area where we re-illuminize our primary mirror segments. On the top floor in that part of the building, that's where we have the control room from where we control this telescope during the night. Okay, next slide. So that just shows a picture, of the telescope on the inside of the building. It is a huge telescope. That primary mirror that you can see there, sort of at the bottom in that structure, is 10 meters, well, actually 11 meters in diameter. So it's kind of difficult to get the whole telescope into one picture. But you can make out there the primary mirror, and in those black boxes on the left and right of the primary mirror, those are the virus spectrographs that we use for our dark energy experiment. And then the black mechanism that you can see at the top of that picture, that is what we call the tracker. And that is the instrument that tracks a star as it moves through the telescope's field of view. And then obviously all those tubes that you see there, that forms a telescope structure that rotates to point the telescope to the object that we want to observe. Okay, next slide.
All right. So actually, the question came in for you from Charlie Ondrech. Apologies, I'm not pronouncing that correctly. Are the 91 segments aligned each night or multiple times at a night?
Yeah, so we do align it every night. The first thing that we do when we open a telescope is point the telescope to that tower that I pointed out, and then we do the mirror alignment. It depends on the temperature conditions during the night. If we have a very temperature stable night, we can go long, we can probably go through the night without realigning the primary mirror. But if there's a sharp temperature change, then we will see that in the image quality of the telescope, and we have to go back and realign the mirror, primary mirror. Typically, we do realignment twice, maybe 3 times a night. Stephen will know better, but it depends, on environmental conditions and how it changes during the night.
Okay, thank you.
Okay, next slide. Okay. So I just list there, a bunch of the kind of technologies, that we have on the telescope. It's a pretty complex telescope, like most telescopes. It's complex instruments. But from an engineering perspective, you may have seen on my first slide, I called it the Hobby Eberly Telescope Engineering Playground. And that's literally how we feel as engineers about this place, because there are so many things that get together to form a telescope. We have mechanical engineers, electrical engineers, we have optical experts, software engineers like Jim himself, is our software team lead. We use cryogenics, to cool things down. We re-illuminize our own primary mirror, our mirror segments with our own coding facility. That is called the vapor deposition process. We have complex instrumentation, control systems, you name it. So for those young engineers out there, or yes, people who aspire to become engineers, this is the ideal place to come and work, because there's endless opportunity to learn things and participate and live out your interests. Okay, so on the next slides, I'm just going to show a couple of pictures. So our team here is primarily responsible for maintaining the telescope, making sure that the telescope works well at night when we hand it over to the night staff. That's when Stephen and his night staff team take over, and collect the science data. But apart from maintaining the telescope, we also do engineering design here at the telescope. Our own staff do mechanical design, design work, all kinds of design work. And I basically just have 2 pictures there, that shows the computer-aided design. The left is one of our guide probes that was actually designed by colleagues in Austin. And the image on the right is an actuator that we that we're busy designing here ourselves, our team here. That is for an upgrade in that CCAS tower that I mentioned. We are designing a new instrument that go up in that tower. Okay, next slide. So this just shows some of the complex mechanical subsystems that we have on the telescope, and this was part of the redesign or the upgrade of the telescope that we performed. Sort of started in 2008. Jim may have talked about that, in his history talk. That we upgraded the telescope to do this dark energy experiment. And for that, we had to redesign a whole bunch of mechanical subsystems. We sort of started with the optics on the telescope, and then it just snowballed, and everything had to be bigger and beefier. And what you see there on the left was the tracker when it was designed. That was done by the Center of Electromechanics in Austin, part of UT. But you can see now it's a huge piece of hardware compared to the people sitting there in the front. The picture on the right is the hexapod that we have on top of the telescope that we use to focus the telescope and align the so-called the corrector on the telescope, the spherical aberration corrector. That has to be aligned with the primary mirror, and we have that big hexapod on there. It's kind of hard to realize, from the picture how big that thing is, but believe me, it's pretty huge. Okay, next slide. So this just shows some more of the mechanical subsystems. The picture on the left is our guide probe assembly that sits on top of the telescope. So typically the optical path of the telescope comes through the center of that assembly that you can see there. And that is where our focal plane assembly would sit, where we then collect the light that goes to our spectrographs. Those probes, sort of in the area around the optical path of the telescope, is where we will pick up guide stars to guide the telescope and do guide corrections. Two of those probes are called guide probes to do that guide correction, and the other two are wavefront sensors that we use to keep the image quality of the telescope stable, sort of do focusing and so forth. The picture on the right is just a picture of the what we call the primary focus instrument package, or PFIP for short. That is where that guide probe assembly is inside there. And at the top of that thing, you can see there's sort of two ears that come out at the top. That's where the optical fibers go into the focal plane when it's on the telescope. Okay, next slide.
So actually, another question came in for you, Herman, from Alan Sunny D. I love the CAD design work. What program is used for this?
We use primarily SolidWorks, but we also have Inventor and AutoCAD, and there may be one or two others, but those SolidWorks is primarily, and also Inventor is what we use.
Thank you.
Okay, so I mentioned the electrical subsystems, for those people interested in electrical engineering. What you see there on the left is our 500 kilowatt emergency power generator. We can basically go completely off grid. If we have a power failure, we can start up that generator and we can continue our science operation as if nothing happened. So we can be totally independent from the grid. The picture on the right, it just shows one of the electrical cabinets that we have in the telescope. That one particularly controls that tracker that I showed in the previous image. All the servo amplifiers that move that tracker, all those servo amplifiers sit in that cabinet. There's actually another one that drives that hexapod, but I can only show so many pictures. I can keep you busy the whole night with pictures of this place. Right, next one. Okay, so optics. I mentioned that obviously a telescope has to have optics to work, and that picture on the left shows the mirrors that are in the spherical aberration corrector. That is probably one of the most complex optical subsystems on basically any telescope in operation at this time. It's all those mirrors are aspherical mirrors and had to be very precisely aligned to produce the image quality that we need on the telescope. That whole optical assembly was designed and assembled by the University of Arizona. And after it was aligned there, we had to put it on a truck, drive it out all the way here, lift it off, check, that none of the alignment got disturbed before we put it on the telescope. So that is the crown jewels, apart from the primary mirror, the crown jewels of the telescope, and very high precision optics and very, as I say, very complex optical design. The pictures on the right show what the focal plane looks like. So the picture at the top shows the front of the focal plane, and those little squares that you see there are the optical fiber cables where the light goes in and then go to the spectrographs. I forgot the number now of how many fibers are in each of those fiber bundles. It's 2,000 plus something fibers. In total, we have something like 35,000 fibers in that focal plane that that we use to collect the science data. So if you think about it, before we did this upgrade on the telescope, we only had single target instruments that could only look at one object at a time. So we could take a spectrum of one object that we pointed to. With the upgrade on the telescope and with that big field of view and on that focal plane, we can, if in theory, if you can get a star on each of those fibers, we can get the spectra of 35,000 objects at the same time. Obviously, in reality, we're not going to get a star on each and every fiber, but whatever falls in that on that focal plane of the telescope, we can get a spectrum of that simultaneously. So you will see stars, galaxies, and whatever is in that field, we can get a spectrum of that all simultaneously. The picture at the bottom shows the back side of the focal plane assembly, and you can see how the optical fibers plug in. So there's still a few short when we took this picture, but that is where these optical fibers plug into the back of the focal plane, and then from there it goes down the sides of the telescope to the spectrographs that we have in those black boxes that I showed on one of the previous pictures. Okay, next slide. Okay, so I talked about the mirror coding, that we do our own mirror reluminizing here at the telescope. So we have 91 segments. Roughly once a year, we have to remove each and every segment from the mirror array, strip off the aluminum coating, and deposit a new aluminum coating. Now, unfortunately, I couldn't get a picture in time of a freshly coated segment. So that one that you see there is a mirror after it's been sitting on a telescope for a year. So, the telescope is open at night, so it's exposed to West Texas. So we get moths, bats, whatever, that come into the telescope, and some do their business on our mirror, which we don't like. But eventually, after a year, that coating is at the point, where we have to strip it off and put on a new coating. So that is an ongoing process. We try to do on average 2 segments a week. That takes us about a year to go get through the whole mirror array of 91 segments, and then it starts all over again. So it never ends. The picture on the left just shows the pure water system that we have. We generate very pure water that we use to rinse off the segments when we first thing that we do is we put acid on the mirror segment to heat off the aluminum coating. Then there's all kind of scrubbing with special chemicals and soaps to clean the mirror substrate. And then we rinse it with the pure water that we get from that system. That is the purest water that you can get. There's only hydrogen and oxygen in that water. All the rest of the stuff has been removed, So Water that pure basically becomes more of like a solvent, so it also helps us to clean the mirror segments. The picture on the right just shows part of the back of the coating tank, vacuum coating chamber, where we put the segments in to coat them. That just shows vacuums, vacuum pumps. So all this is to make the point, that we have all kinds of technologies that work together to make this telescope work. I often tell people, there are so many things in this telescope. There are so many things that can go wrong. It is a miracle every night that this telescope works. And believe me, every night is a miracle. So this telescope is actually pretty reliable and works well. We often go multiple nights without problems. So right, next slide. Okay, so instrumentation. No telescope is useful without sophisticated instrumentation. And here I just show two of our instruments. The one on the left is the so-called HPF instrument, the Habitable Planet Finder instrument, that was designed and built by our colleagues at Penn State University. There, the instrument was still in their lab in Pennsylvania, and then they shipped it out, and it went into the basement of the telescope, where we use that now to find planets around other stars. The picture on the right is just shows the inside of one of our virus spectrographs. Each virus spectrograph has two CCDs, basically two camera chips. And you can see the two there in the two arms that goes out. There's a CCD on each of those. And they connected to a, I don't know if you can see that, but on the picture you can see some copper bars there. That is to cool the spectrograph. You can see there on the front, there is a opening where we put a cryogenic cold finger in, and that would cool down the CCDs to a temperature of minus 110 degrees Celsius. We use liquid nitrogen to do that. And the reason we cool down the CCDs is to improve the signal to noise. Once you cool down those CCDs, you drive the noise level way down. And then the very faint object, stars or galaxies that we look at, will stand out above the noise. So eventually that thing gets enclosed and in a vacuum enclosure that we call a cryostat. But just to show that there are pretty complex instruments that we design. That was designed by our colleagues in Austin, and we have 80 of those spectrographs, 78 for the virus instrument, and two of those that are very similar, only the optics different inside, and that is form our low resolution spectrograph. Okay, next slide.
All right. Actually, another question has come in for you. Yeah, another one from Charlie. Are CCD detectors more appropriate for this application than CMOS detectors?
Yeah. Well, the CMOS detectors, and Jim, you and Stephen should help me here. I believe they operate at room temperature, and that is typically not suitable, for these observations that we do. You just don't get the very, very small signals, that signal to noise ratio that I was talking about. So these are very specialized CCDs that we use for our application.
Can I add just one quick thing?
Sure.
The HPF, the Habitable Zone Planet Finder, works in the near infrared. So CCD silicon is not very sensitive to that. So we actually don't use a CCD there. When they were developing the James Webb Space Telescope, it works in the infrared. They developed a new kind of detector that's made with a different semiconductor. It's a mixture of mercury, cadmium, and telluride. And they designed it for space, but we're also using that same detector, a copy of that same detector in our instrument, because CCDs just weren't good enough in the near infrared. So it is very specialized application. Yeah.
Thank you, Stephen. Okay, so next slide. Okay, so I mentioned, that we have to cool down these CCDs to very cold temperatures, and for that we use cryogenics. On the right, that image shows our liquid nitrogen tank. That is a 11,000 gallon liquid nitrogen tank. When it was delivered to the site and installed, we actually had to get 2 cranes on site to lift that tank off the truck. And then the 2 cranes tilted it upright, and then the crane that grabs it on the top lifted it actually over the building and put it down on the concrete pad behind the building. The picture on the left just shows the cryogenic installation for the Habitable Planet Finder instrument. That dewar or tank that you see there, we refer to that as a dewar, gets filled every couple of days with liquid nitrogen from that big 11,000 gallon tank. And that is an all automated process. The system will automatically detect, when it needs to fill that dewar. And then every day we transfer liquid nitrogen from that dewar into the instrument, which is behind that cryogenic system. That instrument is the Habitable Planet Finder instrument is very temperature sensitive. So it is in a controlled environment, and we try to control the temperature of the instrument to a millikelvin stability. So, it is a very sensitive instrument, and it's one of those instruments. It's in that enclosure at the back there, and we don't even go in there. We only go in there if it's absolutely necessary, when there's something wrong with the instrument, and that rarely happens. But so even when we fill it during the day with nitrogen, you'll see small changes in the temperature, but not so much, that it's a problem. But just to make the point, that that instrument is very, very temperature sensitive, and we handle that with care. We obviously use a lot of nitrogen to cool down our spectrographs. That's why we have 11,000 gallons. We get 6,000 gallons of liquid nitrogen delivered basically every 2 to 3 weeks. We get a truck of 6,000 gallons out here and dump it in that big tank. Okay, next slide. Okay, so I mentioned, this engineering playground. We have so much fun here that we always think we're on cloud 9, and sometimes we physically are.
All right, thank you so much. Now to talk a bit more about some how it looks like when these instruments are working and some of the data that comes up to it, I'm going to pass it over to Dr. Stephen Janowicki.
Yeah, I think so. Let me get a screen ready to share. So you've gotten an overview of all of the amazing technical engineering that goes on at this telescope, and ultimately what all of that is supporting is the science that we do, in particular the instruments that we use and the observations that we make. So on a good night, when we're up there observing, we don't have to think about all of the complexity and layers of subsystems that are going on underneath. We just use the telescope and it works. So I'm going to tell you a little bit about the main instruments that we use and show you some samples of the kind of data that we get from them. So this is just a quick look at our virus spectrograph. I wanted to tell you that it stands for Visible Integral Field Replicable Unit Spectrograph, and it was a very clever name until a few years ago. But there's many copies of that spectrograph, so that's why it's called virus. And as Herman mentioned, it's a series of fiber optic cables that carry light from the focal surface of this telescope down to the spectrograph, and each of those fibers measures the spectrum from a different spot on the sky. And if I do my screens right, I can show you. Oh no, first I wanted to show you this picture again. And I think I got, oh, I didn't get the high resolution one. Anyway, you can sort of see that those are the individual fibers that are collecting the light. So when we observe a patch of sky with that, we get a spectrum from every single one of those fibers. And if we observe, a really big galaxy, like this is Messier 101, I think. We can put together many, many observations. You can kind of see the pattern that we're observing here, these grids that kind of overlap. Those are our little squares observing across the sky. We can eventually construct an image or something that looks like an image where we take the light from each fiber and make it just a single pixel on here. But the real power of this instrument, let me open up this other one. The real power of this instrument is that each pixel, each little fiber, isn't just telling us how much light there is, but it's telling us what spectrum is at that position. So these aren't just pixels in an image. Each pixel gives us a full spectrum. We've broken up the light into all of its colors, and we know how much blue there is and how much red there is. So with this observation of this beautiful spiral galaxy, if we zoom in on just that little pixel right there, where you see that bluish dot, well, this is the spectrum of that object. This is the sort of the fingerprint, the chemical signature of that. And astronomers know from looking at a lot of spectrum that when you see this pattern of these kind of V-shaped lines, that's a rapidly rotating white dwarf, which is a remnant of a star like our sun after it's burned out and dead, spinning really fast. So, okay, if you had just looked at a picture, you'd say, oh, that's a little dot. But when you have a spectrum of it, you can determine it's a white dwarf. The size of those V's in the spectrum tells you how fast it's rotating. Faster ones have bigger V's, and slower ones are tighter. So we've learned a lot about stars from their spectrum. This little dot over here, looks kind of the same. Another little dot. Well, its spectrum is mostly empty except for this one crazy big, huge line in the middle, and that's because, as we've learned, that's a galaxy halfway across the universe from us with a black hole at its center that's eating up material really fast and glowing really bright. And we can identify that from the spectrum. So I think there's a couple more examples. Yeah, you can find star-forming galaxy spectra, and then you can even find some things that are in this galaxy, right? And nothing I've told you so far is actually the galaxy that we're talking about, but that has lots of interesting star-forming regions, and each of these bumps in this spectrum tells us that there's a different element present in that star-forming region, and we can get the temperature, we can get the chemical composition, and the dynamics of the system from these spectra. And like Herman mentioned, we get 35,000 spectra at a time, so we can very rapidly build amazing data sets. The upgrade that Jim mentioned that we did about 7 years ago was motivated by building this spectrograph and doing a survey to look for the effects of dark energy in a very distant part of the universe. And this is the Hobby Eberly Telescope Dark Energy Experiment, and we've been doing virus observations for years for that, and it's coming really close to reaching completion, where we're going to measure how fast the universe was accelerating in its expansion at a very high distance. And that's a virus in a nutshell. It's an amazing spectrograph. There's no spectrograph as powerful as this anywhere else in the world. It's an incredible instrument, and it's doing amazing work. So let me switch to the next instrument here. Okay.
And so a question actually came in about the spectra.
Oh, sure.
These spectra tell you if the point is red shifted or blue shifted.
Yeah. Let me bring this back up. So we are lucky in a sense. We're lucky that the same laws of physics that work on the Earth also work everywhere else, as far as we can tell. So we know what chemical produces this absorption line feature. We know exactly what that is. That's hydrogen, right? So we know a lot about hydrogen. And we can put hydrogen in a laboratory, and we can shine light through it, and we can see what colors get absorbed. And we can measure those to high precision. And so we know if the gas is not moving, if you're doing it in a laboratory and it's not moving, that's what color it should be. So if we see it in a galaxy or in a star far away, if we see it at a different color, slightly Doppler shifted, either it's coming towards us and the light gets a little bit compressed and bluer, or it's moving away from us and it gets stretched out and redder. If we measure that difference in the color, yeah, we can figure out if it's redshifted or blue shifted. Yeah, good question.
Thank you.
Okay, let me show you. I don't remember if this is the right page. Our next instrument that I wanted to show you is kind of a copy of Virus in a sense. It uses a lot of the same parts. It also has fiber optic cables that sit on the focal surface, and they take the light down to a spectrograph. But in this case, it's a very wide wavelength coverage, so we can see light from just beyond the blue end of what our human eyes can see to just beyond the red end of our human vision. So this is really a very powerful general purpose spectrograph. And these are some of the components that go into it. It's another amazing instrument. This is what it actually looks like on the telescope. Those are the little fiber optic cables, and they're all bunched right up together. So when we take an observation here, it has only a couple hundred fiber optic cables, and it covers only a very small patch of the sky, but we get a lot more spectral information when we observe with the low resolution spectrograph. And we have lots of people who use the low resolution spectrograph, but I'm going to tell you about what I do with it, because in addition to being the science operations manager here, I'm also an astronomer, and I get to use the telescope for my own projects. So my research focuses on small dwarf galaxies a lot smaller than our Milky Way galaxy, and looking at the connections between the hydrogen gas that forms new stars and the chemical composition of those galaxies. So how are they growing? How are they using their gas to form new stars? And getting spectral observations of those galaxies is the best way to learn about that. So this is a patch of sky like any other, but it happens to hold one of these galaxies that I study. It has a big cloud of hydrogen around it that we can't see in this optical image, but you can see some kind of clumps and interesting signatures. Those are star-forming regions in the galaxy where new stars are being born, kind of like big versions of the Orion Nebula. These are star-forming regions. And you can learn a lot from a picture. You can understand that it's blue, that means there's hot stars, and it's an active area. But let me show you a spectrum that we took of this. So this is going to get a little technical, so hang on here. But this now, if you remember, I showed you that picture of the fiber optic cables, and they kind of made a rectangle, and there was like a grid of fiber optic cables. This shows if I take all the light from all the cables, or I take the light from all the colors, and I flatten it into just an image. So this is actually my observation of this clumpy galaxy, but where all the colors are compressed together to be the same. As I move my mouse cursor over it, you see that spectrum is updating in real time, and it shows me what the full spectrum is. This is the this is the blue end of the spectrum and the red end of the spectrum. So as I move around, I can see this kind of lump here is just sort of flat, noisy, but this lump here has these, huge emission lines. Like this one down here is especially strong. That's hydrogen again. Hydrogen turns out is everywhere. This line over here is from oxygen, and that's what I'm especially interested in, because as stars evolve, they produce more oxygen. And so if you look at how much oxygen there is, you can figure out how old the galaxy is and how much evolution has happened. So this is an example where it looks just like a picture, but actually every pixel is a whole spectrum, and so we can measure that spectrum across the whole galaxy. Which is very powerful. I mean, this has I use it to look at the chemical composition of galaxies, but other people use it to look at the rotation of galaxies, because in bigger galaxies you might see one side of the galaxy coming towards us and one side going away from us. This galaxy is too small to have a measurable rotation like that. But this is some real data that we took. I guess this one was from about a year ago, but I'm almost finished with this observing program. My survey is almost complete. So look for an exciting publication about star-forming galaxies coming out soon. Okay, let me pull these off, and I'll tell you about the last instrument, which is the Habitable Zone Planet Finder, which, as Herman mentioned, I think is our most sensitive instrument in every sense of the word. It's an extremely high precision spectrograph. But that means it's extremely picky about its conditions. It needs extreme temperature stability. It's too big to put on the telescope. Like we've talked about, the Virus and LRS 2 instruments ride along with the telescope. Well, that would be too bumpy and too disturbing for it. So we have it down in the basement where one fiber optic cable feeds it light all the way downstairs in the basement. And it's extremely high resolution. It breaks up the light into a rainbow, but it's not just like the rainbow you see on the sky where red and blue are like that far apart. It would be like a rainbow, bigger than the sky. It's really spreading the light out extremely far to give us a really high resolution view of a star's spectrum. And what we get, I'm going to show you some raw data. I don't know if that's what people normally do, but here's a behind the scenes look. What we get right off the telescope is an image that looks like this. So each stripe is a spectrum. Each of these white stripes is a spectrum from a star that we're looking at, and it's broken up into different colors. So the colors up here are kind of the bluer ones, and the colors down here are the redder ones. You can see some absorption lines. I could zoom in on these. See these missing colors here where there's kind of black spots between the starlight. Most of those are water vapor in our atmosphere that block the light. So we can correct for that and remove those. And then after it gets processed and we remove all of those atmospheric effects, we get spectra that look sort of like this. So to the average human, this may not look very exciting. I won't be offended if you think that. But to the astronomer, this is an incredibly precise measurement of the light from the star. So these little bumps and wiggles that you see are all different chemicals in the atmosphere and the upper layers of the star. And we know, just like we know from hydrogen, what color those should be. We know where they are in the spectrum, and then we can measure the Doppler shift of this star to extremely high precision. Because I guess, yeah, I didn't tell you, we call it the Habitable Zone Planet Finder because it's trying to find and study planets orbiting other stars that are in the habitable zones of those stars. And a lot of these planets are actually discovered by other telescopes that wait for the planet to go in front of the star and block it, and the star gets a little dimmer. And then we go back with our spectrograph and we study the motion of that planet around the star. And if you know how fast the planet's going around the star, you can figure out how big the planet is, how much mass the planet has. Is it a Mercury or is it a Jupiter? Kind of a big difference for planets. And I think I can show you what that looks like. This is an example of a recent publication from one of our colleagues at Penn State, who was looking at TOI 3757, everybody's favorite exoplanet hosting star. But it's a great one. So this blue curve up here shows this axis is on days, so those are many months of observations. This is basically our model for how the planet goes around the star. And when the planet's on the side of the star coming towards us, it gets Doppler shifted, a little bit blue shifted, and as it's going away from us, it gets a little bit red shifted, and that's what this blue theoretical curve is showing. And all of the green points are nights that we observed this star with the Habitable Zone Planet Finder. And we measured precisely what that velocity, what that Doppler shift was. And we have to do that a lot because you can see we kind of just hit random parts of the curve over time and gradually fill in a full model of that star's orbit, or that planet's orbit around the star. So with, this was maybe 6 months of data. With that kind of a data set, we can really say, it's an Earth-sized planet or it's a Venus-sized planet. I think this one was more like a Jupiter-sized planet, but we can carefully measure the masses of exoplanets and understand if they're gas planets or rocky planets, and understand more about the chances for life, which is what this instrument is all about. So I think those are all of my pictures. A quick overview with some real data of what we get off the telescope every night. So.
That's super cool. Thank you so much. Yeah, so now it's time for Q&A. So if you all have any questions, feel free to submit in the chat. And one did come up earlier, but I felt it would be nice to save it towards the end, so kind of like a group answer of sorts. From Steven Yanagisawa, it seems like technology is changing so fast. How does the equipment and the people keep up?
Yeah, if I can jump in there, we have a range of equipment, of different ages here at the telescope. Jim can also chime in on that. We have computers here that still run Windows NT, and we have to maintain them. And we have some of the most modern computers here as well. Obsolescence is a continuous battle for us. We always busy upgrading something because it's not available anymore. So it's a full-time job. That's why we have a team of engineers and technicians here to maintain this telescope. So apart from making sure that it works every night, we also have to keep up to date with technology. So we often have to upgrade systems on the telescope.
I would say that's also why we do the upgrade projects and why observatories build new telescopes. The older telescopes become obsolete, the older instruments become obsolete. While they're still productive, they're not as scientifically interesting. The new science that you can do. Stephen mentioned the infrared detectors. They came out in the mid-1980s. Before when I was in graduate school. Observatories are constantly defining new instruments. The upgrade project on this telescope occurred in 2014. We were about 14 years old for the older instruments, and we replaced them and put new instruments in it, did new science. We improved the telescope itself to get a wider field of view. And even the construction of the Hobby Eberly was an answer to new technology. The older telescopes were difficult to maintain. They weren't as big as telescopes at other observatories, and we wanted a big telescope, so we built the Hobby Eberly and put the instrumentation on it and upgraded that instrumentation. That's how basically we get around new technology. And as Herman said, we're constantly upgrading the equipment in small ways as well.
I can maybe add, that there's also a financial side to that. We can, from our operating budget, there's only so much that we can do, so we will replace and upgrade, smaller items that are obsolete. But then every so often, you have to do a major upgrade, and that's where we did this upgrade on the Hobby Eberly Telescope that Jim was talking about. Partly because, the telescope was getting old and we need to do new things, but also because there's new science objectives. If there's a good use case or a science case, for an upgrade, then we will find funding to do a major upgrade, to support that specific science. And that's what we did for this dark energy experiment.
Just one particular new piece of technology, or relatively new, that I think is amazing on the Hobby Eberly Telescope are our wavefront sensors, which are not groundbreaking or earth-shattering, but it's a little tool that we have. We have guide cameras to keep the telescope on target, aligned in the right position on the sky. But a wavefront sensor, as a simple-minded astronomer, it just feels like magic because it can split up the light that's coming off the primary mirror. It can split that up depending on which mirror segment it reflects off of. So with this little tiny lenslet array, this little grid of subapertures, we can actually decompose the light coming to the focus of the telescope based on which mirrors are reflecting it. And then we can use that information and the relative alignment to figure out, are we out of focus? Are we in focus? Do we need to tip? Do we need to tilt? How do we need to align this? So the original design of a lot of telescopes, the focus is just done by eye. You kind of twist the knob and see if it gets better, and if it gets worse, you twist it the other way. And that's not a very efficient use of precious telescope time. With a wavefront sensor, like we have two of, that we use every night, you get an instantaneous measurement of where is your focus, where is your alignment, and then how do you correct it in real time. So improvements like that have made the upgraded HET significantly more efficient. We're delivering better science. We're spending less time fixing the telescope and tweaking everything into position, and we spend more time with our shutter open, just collecting photons from the distant universe. And so hopefully that's what the new technology always lets us do, is get better and better. And the same folks that built these instruments are helping build the instruments for the Giant Magellan Telescope, using the lessons learned so far. And so we're taking this big telescope knowledge to bigger and bigger telescopes. It's very exciting.
Yeah. Another question from Charlie. Does the James Webb Space Telescope use the same alignment instrument? Any of y'all happen to know the answer for that one?
Well, you might know that James Webb Telescope does not have an alignment instrument. They use their science instruments to do their alignment. It was a very clever design, but some of the night staff and I were following the commissioning updates from the James Webb Space Telescope, because as they unfolded and started aligning their mirrors, the types of diagnostic images they took to align their mirrors look exactly the same as what we take every night on the telescope. They have the same kind of way to split up the incoming light into the separate reflections. They get a little grid of spots, and they have to figure out which ones go where and keep them all aligned. And so we all watched the commissioning data with great interest, because it looked like a normal night of work for us. But they're in space, right? So they don't get temperature swings like we do. So the mirror doesn't get hotter or colder. And so once they've aligned it, I don't think they have any active feedback control. They just put it into a shape and it stays there. Our mirror is actively aligned, so it's a lot harder. Also a lot bigger. Nothing. It's not a 10-meter telescope. So.
Let's see if there are any other questions that come on in. Doesn't seem to be any more coming in. So want to thank y'all for joining in with us tonight, and thank you, Jims, Herman, and Steven, for joining in. Really appreciate y'all taking time out to join in on the program. It gives some really cool information. And yeah, so if for anyone that's watching, this will be saved onto the YouTube channel, so you can rewatch it later on. Feel free to share it with people so you learn more and celebrate the HET's birthday. And yeah, thank you for joining us tonight.
Sal, you have one question.
Oh, yeah. Oh, thank you for catching it. I had missed it. Yeah. From Charlie. Kitby experienced wildfire this summer. Has protocols changed at McDonald as a result to protect the telescope's buildings and humans?
I can answer some of that. We went through our own wildfire in 2011. You might have seen the picture of the Hobby Eberly Telescope surrounded by fire. We were closed for those nights for soot and ash, and also smoke in the sky, so we couldn't see the stars. Our protocols for observing didn't change because of the fire. We still closed for dust and clouds, just the same. Some of our protocols for safety at the site and how we keep the telescope safe. Yeah, there's a picture of the Rock House fire in 2011. So the observing protocols didn't change, but our safety and life safety and equipment safety protocols did change.
There was another very nice picture, with Burning Mountain right behind the HET. I don't know if that one is available. It was a kind of cool picture.
Should be in here as well.
Frank C's picture.
Yeah, I'm sharing it, so if you can use my.
Oh,
screen.
okay, yeah.
Yeah.
Yeah, there you go. There's the Hobby Eberly Telescope.
Yeah.
Looking north, and Black Mountain in the background, burning, and Sky Peak to the left of the telescope building has already burned. That was a 300,000 acre fire, 330,000 acres. And it burned for 30 days in Jeff Davis County.
I think that was kind of our wake-up call that we needed better fire protection on site as well. That triggered some serious upgrades to the facilities.
There was an upgrade to the water supply to Mount Folks, where the HET telescope is, so that we can get more flow in case of a fire.
Yeah.
Maybe on that topic, we can mention, that we are currently working on a upgrade of the HVAC system that we use to condition the dome during the day. And part of that upgrade, because the Hobby Eberly Telescope sits on the edge of a cliff, sort of a cliff there where you can see in that picture. And on the other side of the telescope, we actually plan to install a sprinkler system as part of that upgrade to the HVAC system that would pre-wet the area should there be a fire coming up that slope.
Yeah.
The wildfires have been a wake-up call for many observatories.
Yeah.
We've
Can
all
imagine.
experienced additional wildfires with the growth of grasses and trees in the areas around the telescope that have not burned for many years. But at least we don't have earthquakes and volcanoes like Canary Islands do.
That's true. A few less things to worry about. All right, let's see if any more questions come on in. Haven't really seen any others coming in, and nothing else from the mods. Yeah, so again, I want to thank y'all for joining us tonight. It's a really fun program, and hopefully y'all can join us for our next stream. Have a good night.
Thank you. Bye-bye.
Bye.